Welcome to the deep dive. Today we're venturing into the, wonderfully strange realm of quantum mechanics.
It really is something else.
Yeah, and our trusty guides for this journey are the legendary Feynman Lectures on Physics, Volume 3, and The Illuminating Theoretical Minimum by Leonard Susskind.
Two classics, definitely. Different styles, though.
Right. And for you, our listener, your learner here, our mission is, pretty straightforward. Extract the core insights, those real aha moments.
The bits that click?
Exactly. The bits that make you see the universe a little differently and give you a solid handle on this fundamental theory without getting sort of bogged down in all the heavy math.
Though some math is unavoidable, fair warning.
True. Okay, let's unpack this.
Well, what's fascinating right from the start is how both Feynman and Susskind, these giants, approach this pretty mind-bending subject.
How so?
Feynman, in his lectures, he kind of starts with certain expectations, doesn't he? About what his Caltech students already knew.
Right, things like basic geometrical optics, simple chemistry ideas. He assumes that baseline.
Yeah, and he also doesn't shy away from introducing big concepts, like qualitatively first, before the deep math dive.
Oh, like inductance or energy levels in atoms.
Exactly. He touches on them early, gives you a flavor, then circles back later for the full treatment.
It's interesting, too, he points out this volume doesn't have dedicated problem-solving lectures. Those were recitation sections, right?
Handled separately. And apparently one whole lecture even got cut, he mentions.
Which is kind of funny. But what really struck me was Feynman's own sort of pessimism. He wasn't totally convinced his teaching experiment here was a huge success.
That bit is quite telling, yeah. It just highlights how tough it is to really convey how revolutionary quantum mechanics is.
Absolutely. And maybe the best place to see that revolution is right at the heart of it, that fundamental puzzle, the two-hole experiment.
Yes, the absolute core mystery.
Okay, picture this. You're firing tiny particles, let's say electrons, at a screen. And this screen has two little slits in it.
Okay.
Behind that first screen, there's another one, a detector screen, that shows where the electrons land.
Got it.
Now, if you close one slit, say slit 2, and just leave slit 1 open, you see a pattern where the electrons hit. A probability distribution, let's call it P1.
Makes sense. A blob behind slit 1, roughly.
Close slit 1, open slit 2, you get another pattern, P2, another blob behind slit 2. Simple enough.
So far, so classical. Little bullets going through a hole.
Exactly. But here's where it gets really weird. You open both slits.
And you'd expect the pattern P12 to just be P1 plus P2, right? Just add the two blobs together.
That's what intuition screams, but no. What you actually get is an interference pattern.
Those stripes. Bright spots and dark spots, like when waves interfere.
Precisely.
Right.
And this result just completely flies in the face of our everyday intuition about particles.
Yeah, we want to think, okay, the electron's a tiny ball. It must go through either the left hole or the right hole. It can't do both.
But that interference pattern, it tells us something much stranger is happening. It behaves as if it's somehow aware of both holes, maybe going through both, and interfering with itself.
And Feynman is so clear on this, it's profound. Nobody has ever found the underlying machinery behind this.
Right. There's no deeper mechanism we know of that explains this. We can describe it with math, but we can't say why it works that way.
It's just a fundamental law, as far as we can tell. A huge shift from classical physics where everything's deterministic. Give me the starting conditions, I tell you the future.
Not here. In the quantum world, it's probabilities baked in right from the start. Not certainty, just likelihood.
And this probabilistic nature, this uncertainty, leads straight to another cornerstone, the uncertainty principle. Heisenberg's, though, Feynman discusses it thoroughly.
Ah, yes. The idea that you can't know everything perfectly at the same time.
Exactly. If you try to measure, say, the momentum of a particle in the x direction really precisely, with a small uncertainty,
then your knowledge of its position in the x direction gets fuzzy, right? There's a limit.
Precisely. The uncertainty in position text has to be at least divided by roughly 2 times dVep. So vexadap.
And that's the reduced Planck constant. It's incredibly tiny, like 10 Ural seconds.
Which is why we don't notice this in everyday life. For baseballs, the uncertainty is negligible. But for electrons, it's fundamental.
And it's not just about clumsy measurements, is it? It's deeper.
Absolutely. It's a fundamental property of reality. The more you pin down position, the less you know about momentum, and vice versa.
True.
They're intrinsically linked.
There's a trade-off.
A fundamental trade-off. And the really mind-bending part, the more general statement Feynman makes, is that Any attempt to find out which hole the electron went through.
Inevitably destroys that interference pattern.
You got it. The act of measuring which way forces it to behave like a particle going through one hole or the other, and the wave-like interference vanishes.
Wow. He shows this with single-slit diffraction too, doesn't he?
Yeah, beautifully. Make a single slit narrower, meaning you're localizing the electron's position, small a, as it passes through.
Then the pattern it makes on the screen behind it gets wider.
Gets wider, which means the spread in its momentum in that direction gets larger. It perfectly shows that inverse relationship. Squeeze one uncertainty, the other balloons out.
It's built in. And this isn't just abstract math. It has real consequences, like why atoms don't collapse.
Exactly. Take a hydrogen atom. Why doesn't the electron just spiral into the proton? Classically, it should radiate energy and fall in.
But it doesn't.
Because if the electron were right at the nucleus, its position would be known very precisely. By the uncertainty principle, its momentum would have to be wildly uncertain, meaning you would have a huge kinetic energy, enough to escape.
So the uncertainty principle forces the electron to be sort of smeared out in a cloud around the nucleus. It maintains a minimum energy level.
That's the gist of it, yeah. It enforces a kind of minimum size and stability.
Okay, so reality is fundamentally probabilistic and uncertain at its core. How do we even describe this mathematically? Probabilities alone aren't enough for interference.
Right. That's where probability amplitudes come in. Schrödinger gave us his famous equation, which lets us calculate these amplitudes.
And Feynman notes it looks a bit like classical wave equations mathematically.
It does share similarities, but the physical meaning was the revolution. People like Max Born, Paul Dirac, they figured out the new physical ideas behind the math.
And the key idea is these amplitudes aren't just numbers, they're complex numbers. Why complex?
Ah, great question. Complex numbers have two parts, a magnitude and a phase. The magnitude squared gives you the probability, but the phase, that's crucial.
Like the phase of a wave, crests and troughs.
Exactly like that. The phase allows these amplitudes to interfere, to add up constructively in phase, or destructively out of phase. Regular probabilities just add, they can't cancel out.
Okay, so the complex nature encodes that wave-like interference behavior.
Precisely. And the fundamental rule is, if something can happen in multiple ways, like an electron going through hole 1 or hole 2 to reach a detector.
You don't add the probabilities P1 and P2.
No. You find the amplitude for path 1, let's call it A1, and the amplitude for path 2, A2. You add the amplitudes, a total A1 plus A2.
And then you find the probability.
And the probability is the absolute square of that total amplitude.
Right.
A total equals A1 plus A2 other it. That squaring process is where the interference terms pop out.
Got it. Add amplitudes, then square. That explains the stripes in the two-hole experiment.
Exactly. And this principle applies everywhere in quantum mechanics. Anytime there are multiple indistinguishable pathways for a process.
Like, if an electron bounces off something and emits a photon, you'd combine amplitudes for each step.
You would, yeah. It's the fundamental calculus of the quantum world.
Okay, let's shift gears a bit. Particles aren't all the same, are they? Feynman talks about Bose particles and Fermi particles.
Right. Two fundamental families. He introduces Bose particles, or bosons, by looking at blackbody radiation.
That's the glow from hot objects, right? Like the burner on a stove?
Yep, and the particles of light, photons, are bosons. The key thing about bosons is that any number of identical bosons can be in the exact same quantum state at the same time.
They don't mind piling up together.
They're sociable like that. So Feynman considers atoms with just two energy levels, interacting with photons in thermal equilibrium, basically, in a hot box.
And by doing that, he derives a formula for the average number of photons you'd expect to find in a state with a particular frequency at a given temperature.
He does. The formula is sense equal 1. Equal 1. It perfectly describes the blackbody spectrum Planck figured out.
Okay, but then comes one of those marvelous miracles he talks about.
Ah, yeah, this is beautiful. That formula for the average number of photons, it turns out to be mathematically identical to the formula for the average energy level of a quantum mechanical harmonic oscillator.
Like a mass on a spring, quantized.
Exactly. Or a standing wave in a cavity. Simple oscillating systems. The energy levels of such a system are E, n plus 12, where n is an integer. If you calculate the average n in thermal equilibrium, you get the same math as for the photons.
So somehow a collection of non-interacting photons in a box behaves mathematically just like a set of independent quantum oscillators.
It's this incredible connection. It lets us think about the electromagnetic field either as waves or as these discrete photon particles which behave like excitations of these oscillators. It's deeply weird but powerful.
Okay, so those are bosons. What about the other kind, Fermi particle?
Fermi particles are fermions like electrons, protons, neutrons. They're the opposite. They are governed by the Pauli exclusion principle.
The one we learn in chemistry, no two electrons in the same state.
That's the one. More precisely, no two identical fermions can occupy the exact same quantum state simultaneously. And state includes everything position, momentum, and also their intrinsic spin.
So, unlike bosons, fermions are fundamentally antisocial. They refuse to share the same quantum spot.
You could put it that way. And this principle is absolutely crucial. It's why matter is stable and takes up space.
How so? More than just the uncertainty principle.
Yeah, it's key for bulk matter. You can't just squeeze infinite electrons into the same lowest energy level around an atom. They have to fill up successively higher energy levels, dictated by the exclusion principle.
Ah, so that's what creates the structure of the periodic table, the different chemical properties of elements.
Fundamentally, yes. It prevents atoms from collapsing into each other.
Right.
Prevents all matter from just smushing into one dense blob. It gives structure to the universe.
Okay, exclusion is vital. Now, you mentioned spin. Feynman spends a lot of time on spin, often using these two-state system analogies.
He does. Spin is a purely quantum mechanical property. It's like an intrinsic angular momentum. For electrons, it can be up or down relative to some axis. He often uses the idea of filtering atoms based on their spin, like in the Stern-Gerlach experiment.
Right, sending atoms through a special magnet that splits the beam based on spin direction. Like a filter for plus S spin up or S spin down.
Exactly. And the weird part comes when you chain these filters together, especially if you rotate them relative to each other.
Like filter for plus S, then immediately filter for plus S again, you get 100% through, presumably.
Right. But filter for plus S, then rotate the filter 90 degrees and filter for, say, plus T. Spin up along a perpendicular axis.
Then what? Not zero, not 100%.
Exactly. You get some fraction through. And what's key is that the first filter resets the state. If an atom passes the plus S filter, its state is plus S. What it was before that filter doesn't matter for the next filter.
And the measurement changes the state.
Fundamentally. And Feynman introduces notation for the amplitude of getting one result given a previous state. Like Ore plus T plus S is the amplitude to measure plus T if the state was prepared as plus S.
And if you have intermediate steps, like going from S to R via T.
Then you have to sum the amplitudes over all possible intermediate states. The amplitude for S to R is the sum of amplitude S to plus T times amplitude plus T to R plus amplitude S to plus T times amplitude T to R. You sum over the complete set of intermediate possibilities.
Okay, that sounds like it leads naturally to matrix multiplication.
It does. You can represent these filters or measurements as operators. And for simple systems like spin 12, these operators are 2x2 matrices acting on state vectors.
And properties emerge from this, like orthogonality.
Yeah, distinct base states like plus S and SS are orthogonal. The amplitude or plus SSE is 0. Also, the amplitude to go from A to B is a complex conjugate of the amplitude to go from B to A. SAB equals Ure S.
And he talks about rotating these filters, using Euler angles.
Right, Euler angles are just the standard way to describe any 3D rotation. He shows how the spin amplitudes transform under rotation. For a simple rotation around the z-axis by an angle, the amplitudes get multiplied by a phase factor, e to the power of I times something times phi.
And that connects to polarized light somehow.
Yeah, there's an analogy between the rotation of spin states and the rotation of the plane of polarization of circularly polarized light, which relates to the angular momentum carried by photons. It's another one of those neat cross connections.
Okay, shifting from states to how they change. Time evolution. How does quantum mechanics describe that?
Well, Feynman starts with the free particle. Its probability amplitude at position x and time t, if it has momentum p and energy e, is proportional to that complex exponential.
PEAX.
That looks like a wave. It is, a complex wave. And interestingly, if a system is in a state of definite energy E, an energy eigenstate, the probability of finding it anywhere, amplitude is constant in time, doesn't change.
But things do change. Electrons move. How does that happen?
That happens when the state is a superposition, a mix of different energy states. When you add up those complex waves with different energies and therefore different frequencies, they interfere in time and space.
And that creates lumps.
Exactly. Localized lumps of probability that move. The speed of these lumps is the group velocity, and it turns out to match the classical velocity we'd expect for a particle with that average energy.
So particle motion emerges from the interference of these underlying waves. What about tunneling?
Ah, quantum tunneling. A classic weirdness. Even if a particle doesn't classically have enough energy to get over a potential barrier, like a hill, its probability amplitude doesn't instantly drop to zero at the barrier.
It kind of leaks through.
It decays exponentially, but it does penetrate into the barrier region, and there's a non-zero amplitude, and thus probability, for it to appear on the other side. Completely impossible, classically.
And potentials can bend paths, too.
Yeah, if the potential energy V changes with position, a potential gradient, it acts like a varying refractive index for the probability amplitude wave. It changes the local wavelength, causing the wave, and thus the particle's likely path to bend or deflect.
To handle all this more formally, we need operators, right?
Right. Operators are mathematical objects that correspond to physical observables, like the momentum operator, p hat, which Feynman writes as AII times the gradient. Acting on the wave function gives you momentum information.
And there's an operator for time evolution.
Yes, UT euro, which takes the state at time t to the state at time t. Its behavior is governed by the most fundamental equation of quantum dynamics, the Schrödinger equation.
I duress.
That's the one. It tells you how the state vector Eric changes infinitesimally in time, driven by the Hamiltonian operator H.
And H is the energy operator.
H represents the total energy of the system. If eigenfunctions are the stationary states, we mention states with definite energy E. When H acts on an eigenfunction Eric, you just get E times PE back, Eric E.
And those states just evolve with that phase factor, EIET, so their probability distribution is constant.
Exactly. They're stationary in terms of probability.
Now, Feynman makes a really deep point connecting symmetries and conservation laws.
Oh yeah, this is fundamental. Noether's theorem, essentially, though he presents it intuitively, the idea is that if the laws of physics have a certain symmetry, there's a corresponding conserved quantity.
Like if the laws don't change over time.
Time translation invariance. That implies conservation of energy.
And if they're the same everywhere in space.
Space translation invariance implies conservation of momentum.
And if they don't care about orientation.
Rotational invariance implies conservation of angular momentum. It's a profound link between the geometry of space-time and the fundamental laws of nature.
Beautiful. He then comes back to those two-state systems with real examples.
Right, showing how this simple model applies broadly. He talks about the ammonia molecule, NHE.
The one that can flip inside out like an umbrella.
That's the one. It has two states based on which side of the nitrogen plane the hydrogens are. This leads to energy level splitting, especially in an electric field. It's the basis of early atomic clocks, the ammonia maser.
And the hydrogen molecular ion, H arrow.
Yeah, two protons, one electron. The electron could be near one proton or the other. This possibility of flipping between them lowers the energy, creating a stable bond, a one-electron bond. He calls it a flip-flop energy.
He even mentions pions mediating proton interactions briefly.
Just a nod to nuclear forces, yeah. And then he brings back electron spin in a magnetic field. Spin up or spin down relative to the field B have different energies. Abiz, another perfect two-state system.
And his point is that the math for any two-state system can basically be mapped onto this spin problem.
Pretty much. The underlying mathematical structure is the same, which is why understanding spin is so fundamental.
So to really dig into spin math, he introduces the Pauli matrices.
Exactly. These are specific 2x2 matrices that represent the operators for measuring spin along the x, y, and z axis. He shows how they act on the spin-up state plus A, represented as column vector 1, 0, and spin-down state A key 0, 1.
And they have specific algebraic properties?
They do. And he shows that any arbitrary 2x2 matrix can actually be written as a combination of these three Pauli matrices plus the 2x2 identity matrix. They form a complete basis for 2x2 matrices.
Interesting. He takes a quick detour into particle physics, too, with strangeness.
Yeah, just a brief mention. Strangeness is a quantum number, like charge, that's conserved in strong interactions, like protons hitting protons, but not in weak interactions involved in radioactive decay.
He gives an example with K-mesons.
Right, showing how strangeness adds up and stays the same in a strong collision. He also mentions the weirdness of neutral K-mesons, Curie and antico, which can actually mix into each other via the weak force, violating strangeness, a hint of deeper particle physics complexity.
Okay, back to the familiar hydrogen atom. We said the electron has spin, the proton has spin, so the ground state isn't just one state.
Correct. Even in the lowest energy orbital, the one state, you have the electron spin, up or down, and the proton spin, up or down. That gives 2 by 2 equals 4 possible spin states for the ground level.
And these states don't all have exactly the same energy.
Not quite. There's a very small interaction between the magnetic moments associated with the electron and proton spins. It's called hyperfine interaction. It causes tiny energy shifts, much smaller than orbital energy differences, but measurable.
So he introduces spin operators for both particles and sup.
Yep, acting on the combined state. The interaction energy depends on their relative orientation, described by a term like a times stat sup.
And solving for the energy states of this interaction gives.
It gives you the 4 stationary states. One state, called the singlet state, has the spins anti-aligned, total spin 0, and has 1 energy. The other 3 states, the triplet states, have the spins aligned, total spin 1, and share a slightly different energy.
Ah, the famous 21-centimeter line in radio astronomy comes from the transition between these states, right?
Exactly. That tiny energy difference corresponds to a radio frequency photon. He then looks at what happens in an external magnetic field, the Zeeman effect. The field splits the triplet states further based on their orientation relative to the field.
So the simple hydrogen atom ground state has this rich internal spin structure.
It really does. It behaves like a mix of a spin 1 particle, the triplet, and a spin 0 particle, the singlet, in weak fields.
Okay, towards the end of Volume 3, Feynman starts looking at more complex systems, like electrons in crystals.
Yeah, a really important topic. He asks, how can electrons move so easily through a seemingly dense, solid crystal lattice? That's what makes metals conduct and transistors work.
It seems counterintuitive. Shouldn't they just bounce off all the atoms?
Classically, maybe. But quantum mechanically, we use probability amplitudes again. An electron at one atom has an amplitude to jump or tunnel to a neighboring atom.
So the electron state becomes spread out across the lattice.
Exactly. The amplitudes propagate through the lattice like waves. And due to the periodic nature of the crystal, these electron waves can travel quite freely under certain conditions.
And this leads to the idea of an effective mass.
Right. The electron interacting with the periodic potential of the lattice behaves as if it has a different mass than a free electron. This effective mass can even be negative sometimes. It's crucial for understanding semiconductors.
He even connects this back to the idea of amplitudes in continuous space.
Yeah, he shows how taking the limit of a very fine lattice starts to look like the probability amplitude distributions we use for electrons in empty space, hinting that maybe space itself is fundamentally granular or lattice-like at some level. It's a provocative idea.
And then a brief touch on superconductivity.
Just a qualitative sketch. At very low temperatures, electrons in some materials can form bound pairs, called Cooper pairs, due to a subtle attraction mediated by lattice vibrations.
And these pairs are special how?
They act like bosons, even though they're made of 2 fermions. And since they're bosons, they can all condense into the same lowest energy quantum state.
A macroscopic quantum state.
Exactly. Millions of pairs acting in unison, described by a single wave function spread throughout the material. This allows current to flow with 0 resistance. He also mentions the Josephson junction, 2 superconductors separated by a thin insulator.
And current can tunnel across even with no voltage.
Yeah, the Cooper pairs can tunnel, leading to weird effects like current flow depending on the phase difference of the wave functions on either side. Mind-bending stuff.
Okay, that's a whirlwind tour of Feynman's Volume 3. Now let's connect this to Susskind's theoretical minimum, which sets up the classical foundation first.
Right, Susskind really emphasizes understanding classical mechanics deeply before jumping into quantum. He starts with the basics. Classical physics is deterministic and reversible.
Know the present, know the future and the past, define your system, make it closed, no outside interference.
And then think about the space of states. All the possible configurations a system can be in, and the dynamical laws that tell you how it moves through that state space over time.
He lays out the math tools too. Vectors, components, basis vectors, velocity as the time derivative of position.
Integration is the inverse, finding area under curves. Basic calculus is the language.
And he contrasts Aristotle's wrong ideas about motion needing continuous force with Newton's EFMA.
Crucially pointing out EFMA is a vector equation. Direction matters. And he hammers on the importance of consistent units. You can't mix meters and feet without conversion factors.
Then potential energy, V. Force pushes things towards lower potential energy. And conservation of energy, kinetic T plus potential V constant if no friction or outside forces.
The bedrock of classical mechanics. But then he introduces a more abstract, powerful framework, the principle of least action.
This always felt a bit magical. The path a system actually takes between 2 points in time minimizes this quantity called action.
Yeah, the action S is the integral over time of the Lagrangian. L, and for simple systems, L is just kinetic energy minus potential energy, L equals TV.
Why T minus V? Seems odd.
It does, but it works. Minimizing the integral of TV dt gives you the correct equations of motion, the Euler-Lagrange equations. It's an incredibly elegant principle that works even for complex systems.
And it handles systems with many degrees of freedom using generalized coordinates.
Right. Any set of variables Q's that describe the system's configuration. And from the Lagrangian, you can define generalized momenta P's, which are conjugate to the coordinates.
And just like Feynman showed, Susskind connects symmetries in the Lagrangian to conservation laws. If L doesn't depend explicitly on time, energy is conserved. If it doesn't depend on position,
momentum is conserved. If it doesn't depend on orientation, angular momentum is conserved. Same deep connection viewed through the Lagrangian lens.
Then he introduces the Hamiltonian, H. How's that different from the Lagrangian L?
H is derived from L via a mathematical transform, a Legendre transform. It's expressed in terms of coordinates, q's, and momenta p's, whereas L uses coordinates and velocities, q dots. For many common systems, H turns out to be simply the total energy, T plus V.
And the equations of motion look different too, Hamilton's equations.
Yes, they're a set of first-order differential equations for how Q changes and how P changes over time, often simpler to solve than the second-order Euler-Lagrange equations.
This leads to the idea of phase space.
Right, a space where each point represents the complete state of the system, all its Q's and all its P's. The system's evolution is a path through this phase space.
And Liouville's theorem says
that the volume occupied by a bundle of possible states in phase space stays constant as the system evolves according to Hamilton's equations. It's like an incompressible fluid flow in phase space.
He also introduces Poisson brackets. What are those for?
They're a mathematical tool within Hamiltonian mechanics. They provide a concise way to express how quantities change over time, and importantly, they form a direct bridge to the commutation relations in quantum mechanics.
Ah, a hint of the connection to come. Finally, Susskind tackles gauge invariance in electromagnetism.
Yeah, this is subtle but crucial. In E&M, we use scalar potential and vector potential, A, to describe fields. But you can change A and A in certain ways, a gauge transformation, without changing the actual physical electric E and magnetic B fields.
So the potentials aren't uniquely defined?
Not uniquely. Different potentials can describe the exact same physics. Gauge invariance means that our final physical predictions, like forces on charges, must not depend on which specific gauge, which choice of A and A we used in our calculation.
And the Lorentz force law comes out of this.
You can construct a Hamiltonian for a charged particle in E and M fields that is gauge invariant, and Hamilton's equations for that Hamiltonian give you precisely the Newton-Lorentz force law, F equal QE plus VXB.
So there's this tension. The mathematical description uses these gauge potentials, but the physics must be independent of the specific choice.
Exactly. It's a deep feature of field theories, including the standard model of particle physics. Why the universe uses these gauge fields while insisting on gauge invariance is, well, one of the profound aspects of fundamental physics.
Wow. Okay, stepping back from all that detail, from both Feynman and Susskind, what are the big aha moments we should take away?
Well, for me, it's definitely the sheer inescapable weirdness revealed by things like the two-hole experiment. Our classical intuition just fails.
Yeah, that and the fundamental limit imposed by the uncertainty principle. You just can't know everything precisely. It's not a limitation of measurement, it's how reality is.
And the power of probability amplitudes, complex numbers in coding phase being the real bedrock for calculation, leading to interference.
Also, the deep, elegant connection between symmetries and conservation laws. That feels fundamental on a different level.
It really does. And maybe seeing how these bizarre microscopic rules can actually bubble up to create macroscopic phenomena we can observe, like superconductivity or just the stability of matter itself via the exclusion principle.
Absolutely. Now, if you, our listener, are feeling like your head is spinning a bit,
which would be totally understandable.
Yeah, that's okay. This was a really dense, deep dive into some seriously fundamental and often counterintuitive ideas. Each concept we just skimmed over. Well, you could spend a lifetime exploring its depths.
And physicists do. This is really just scratching the surface. But hopefully it sparked some curiosity. Which ideas jumped out at you? What felt particularly strange or interesting?
If you do want to go deeper, Honestly, you can't do much better than reading Feynman's lectures or Suskind's theoretical minimum directly. They're challenging but incredibly rewarding.
Absolutely. Take your time with them.
So here's a final thought to leave you with. Just consider how profoundly these quantum rules, which seem so abstract, so contrary to our everyday experience, aren't just some theoretical curiosity.
Right. They're not optional extras.
No, they are the fundamental operating system of the entire universe. Everything from subatomic particles to stars and galaxies ultimately plays by these quantum rules. Our classical common sense, it's just a useful approximation that works well for large, slow things. But the deep reality, it's quantum. It's probabilistic, it's uncertain, it's built on amplitudes and interference. It's much, much stranger than we perhaps intuitively feel it ought to be.